Okay, welcome back to our next talk, which will be Eric Swenson from BYU talking about from cuts to trees.
Okay, so here we go. So I've done things like this before, so we'll describe some of the previous work here to start, maybe. Okay, so for a continuum with a cut point, there is a canonical R tree corresponding to the cut points and how the cut points separate the continua. So in this case, we have this simple continua. It's a topologist sine curve together with a couple of arcs, a few circles, and a couple of disks. And the cut points are all in black. All the non-cut points are colored in some other color. So basically, this is the tree that we get from the original continua, where the things that can't be separated by cut points become these little colored blobs. Okay, so that's how you do the trick with cut points. But let's say we have a continua that doesn't have cut points, that in fact is cut by a finite set. So you can cut it by removing a finite number of points. And so here is an example of this. Panos called this modern art. I think his standards for modern art are not high enough. But anyway, this particular continua can be separated by removing 5 points. Okay, and weird sort of things can happen, and I've tried to illustrate the sort of strangeness that can occur. You can see how cuts with 5 points can in fact cross one another, but these sort of are organized into things. And now the corresponding tree looks like that tree down there, right? Okay. So now, if there are no questions, we'll go to the next one. Okay, so now we're going to do a review of undergraduate topology, because that, I'm afraid, is the only thing that I'm going to use in this particular work. I was planning on doing stuff with with bare spaces and stuff like that, but none of it worked. So we're going back to undergraduate topology. A separation of a topological space is a pair of disjoint, non-empty, open subsets whose union is the whole space. For 2 points in the space and a set in the space, we say that the set separates the 1 point from the other point if there is a separation with one of the points in one element of the separation and the other point in the other element of the separation of the subspace X minus A, of course. And now, just to get the notation down, for 2 subsets of our space, we say A separates B if there are 2 points in B which are separated by A. And lastly, for 3 subsets, we say A separates B from C if there's a point in B and a point in C with A separating B from C. This seems like a kind of strange and not particularly well-defined thing here, but trust me, we'll be using it, and when we're using it, it will be well-defined, so it's not so bad. Okay, so now this is our setting. Z is a connected topological space. A is a collection of closed subsets, which we call cuts, satisfying the following conditions. Okay, the first condition, each element, each cut separates our topological space. Second condition, one cut will never separate another cut. The third definition, For distinct cuts, their intersection doesn't separate the space. Okay, now I should mention that two of these conditions are absolutely necessary, and one of them is completely unnecessary. The first condition, it turns out, is completely unnecessary. But the first condition is to keep you from doing insanely stupid things. So at one time, I might have believed that such a condition was unnecessary, but I think the past 4 years have proven that I would have been wrong. Anyway, so the first condition, it turns out, isn't necessary at all, but it doesn't make any sense really to do it without the first condition. So we're doing it with the first condition. Okay, so now under this setting, there is a complete median pretree consisting of closed subsets of Z satisfying the following. So I'm going to define pretree eventually, but for right now, just think of a pretree as being a subset of a tree, right? Where the betweenness relationship on the pretree is just the betweenness relationship on the tree when one point is between 2 points, right? When the arc connecting the 2 points goes through the third point, then the third point is between the 2 points. Okay, so here. So our conditions are that the set of cuts is a subset of this pretree. The entire space is a union of all the sets in the pretree. For two elements of P, C doesn't separate. So these things in the pretree don't separate one another. And now finally, those conditions are kind of just set up. This condition is the real important one. If we have 3 elements of the pretree, and if A and B are not subsets of C, then if C is between A and B, then C separates A from B in the topological space Z. And the second condition then, if C separates A from B, then this is not quite what you might have been expecting. Then there is something between A and B, and this something is a subset of C. Okay. Okay, now a complete pretree embeds in an R tree if and only if the pretree is pre-separable, which I'm not going to define. You're welcome. But I'm just going to give you this condition that implies pre-separability. If any 2 points of Z are separated by at most countably many elements of A, then P is pre-separable. So that's all we're going to say about this. Now, I should mention that pre-separable, there might be some way of using bare category theory or something like that to get pre-separable, but we're not going to do it. Okay, any questions? We ready to go on? Okay, so that's the theorem. So basically what we're saying is that we can form a tree that encodes how these cuts separate things in our space. Okay. All right, now we're going to talk about the pretree. So we're going to talk about the other elements in the pretree. A set is called inseparable if there is no cut which separates it. Okay. Every inseparable set is contained in a maximal inseparable set. That's just the obvious Zorn's lemma argument. You can do it instead of listening to the rest of the talk, or, well, you can probably do it in the next line. Anyway, by our second condition, every cut is inseparable. Some cuts may be maximal inseparable sets, but they don't always have to be. A maximal inseparable set, which is not just a single cut, is called a blob. Script B is the collection of all blobs. And now our pre-tree will just be the cuts union the blobs, okay? So every element in our pre-tree is a cut or a blob. Since every point is inseparable, and every inseparable set is contained in a cut or a blob, then Z is certainly equal to the union of all the sets in P. Okay, so now the betweenness relationship is a little bit subtle. So the first stage of setting up the relationship is easy, right? If we have 2 points, 2 elements in P and a cut, we say that the cut is between B and C if the cut separates B from C. So just exactly the obvious thing you would expect. And now we're going to use this definition that we have here to bootstrap to the next level. Okay, so for distinct A, B, and C in P, with B a blob, we say that B is between A and C if, okay, this pair of half-open intervals in the pre-tree don't intersect, right? Now this seems kind of circular, but it isn't, because we're taking those intervals to be the ones defined above, right? Where the only thing between things were cuts. Okay, are we happy with that? So that's when a blob is between 2 things, is when these intervals don't intersect. Okay, so now the betweenness relation so defined satisfies the axioms of a pre-tree, not very easily, but it's all just, well, in some sense, it's undergraduate topology, so it isn't that hard, but it's not obvious. Anyway. Okay, so now we've talked about pre-trees. Let's actually write down the axioms so we know what we're talking about here. A pre-tree is a structure on the set R. It's a function from R cross R into the subsets of R, satisfying there's nothing between a point and it's or one of these elements and themselves, right? The second one is it symmetric. The stuff between A and B is equal to the stuff between B and A. Now those two are obvious in our example that we're looking at, in our pre-tree that we're constructing. The next two are not obvious. Okay, so this says if A is between B and C, then B is not between A and C. And the fourth one is the interval from A to C is contained in the union of these 2 intervals, from A to B and from B to C. Okay, so if you think about this in terms of trees, this becomes pretty obvious, right? If you have a subset of a tree, then certainly it's going to satisfy all 4 of these axioms, obviously. Not every pre-tree embeds into a tree, simplicial or real, right? But there are conditions that make that happen. Okay, so now let's do an easy example of how we would use such a thing. Okay, so our space is going to be the union of the plane with a half plane that's glued along the horizontal axis. Okay, and now what are our cuts going to be? They are going to be unions of a vertical ray and a horizontal ray. So a vertical ray starting at the point I on the x-axis, and a horizontal array going from I to infinity on the x-axis. So let's So those are our set of cuts. And the picture that we get looks like this. I'm just labeling the vertical part of the AIs. The horizontal parts are just going to the right. Now notice, where are the blobs in this picture? There's a blob between each pair of vertical rays here, right? And there's also the blob at the end, right? So the lower half plane and the glued on half plane, these are all in a single blob. They're in different quasi-components of Z minus all the cuts, but their union is contained in a single blob. And this generally happens. Okay. So that's an easy example. Now, okay, let's talk about the bipartite structure on P, because this is actually the key to understanding, well, doing a lot of the proofs. For any two points in our pre-tree, we say that they're adjacent if nothing is between them. And now 2 points will be adjacent if and only if, relabeling if need be, one of them is a blob, the other one is a cut, and the cut is contained in the blob. So the cut is actually a subset of the blob. And this is the key to showing that P is both complete and median. So complete is the surprise here. I did not expect this to be true, right? I assumed that in order to get completeness, you would have to start with a compact space of some type. It turns out that isn't the issue at all. This bipartite structure forces completeness on you, no matter what the topology of the original space. And that was something of a shock. Anyway. Okay, so now the sharpness of our conditions. The sharpness of condition two is already well understood, right? The point of condition two is, well, the cut's not crossing. This is why they invented cube complexes, right? To understand when cuts cross. That's really what cube complexes is about, right? Understanding the failure of condition two and why you couldn't get a tree from that and all of this. So I'm not going to talk about condition two, but I'm going to mention sort of the sharpness of condition three. Now, so what am I taking? I'm taking a little rectangle, side length 2 horizontally, side length 1 vertically, and then I'm sticking a little tail on top of it. And now my set of cuts are all of the vertical line segments that run up into the tail, starting from the origin. So let's go ahead and give our picture here. Here's our picture. So here is our space Z, and we have a single cut, the cut A 3/2. That's just that vertical line segment. And you'll notice that each of these guys will cut our space into, well, 3 pieces, but 2 of the pieces are significant in the picture, right? So it's clear that Z and A will satisfy our first 2 conditions, but not our third condition, right? They fail the third condition because the intersection of 2 of these cuts will still separate the space. And now we're just going to show that we don't get a pre-tree from this. There are exactly 2 blobs, the left blob called B and the right blob called C, right? And everything is between B and C. Absolutely everything, all of the cuts separate B from C, right? However, if we look at just the shortest possible cut, the one that just goes just up to the top of Z, and we look at the closed interval B, comma A1 union A1, comma C, the union of those 2 half-open intervals, that's just A1, right? So the stuff between B and C is not contained in that union, and so pre-tree axiom 4 fails in this example. So this shows that we can't get rid of condition 3. Now, there was another issue. There's an obvious way to weaken condition 3, right? You would say it this way: for A and B cuts distinct, if Z minus the intersection had fewer quasi-components than Z minus any one of them. That would be an obvious way of weakening that. This is going to fail as well. Replacing 3 with this weaker condition will fail as well, and we'll just do the example here. Okay, so we take 3 unit squares, we take T, a square of side length 3, and we're going to glue one edge of each of the unit squares along the top of the square of side length 3 in the following fashion, right? So we've glued each of the unit squares along the top of this thing of side length 3. And now we take as our cuts the initial interval in the gluing arc of length 2 and the terminal interval of length 2. So this satisfies conditions 1, 2, and the weaker version of 3, but A is between B and S2, B is between A and S2, so this fails Pretree axiom number 3. Okay, so, and that's the last slide, so we're done.
Okay, let's thank Eric. Questions? I'll ask a question. So this was at the beginning and sort of scattered, I think, at other places in the talk. But what was your initial motivation for looking at this kind of thing?
Okay, so it's always the same motivation. What we're trying to do is take the boundary of a group and find a set that separates the boundary, and then construct an R tree on which the group acts, hopefully by isometries, and then apply Rip's machine or Serre's work on trees, fast Serre theory, to get some sort of decomposition of the group. That's what we're trying to do with this. Okay, but we haven't done that part yet. This is what we needed, something like this first before it was even reasonable to proceed with the next step.
Thanks. Other questions? Okay, well, if not, let's thank Eric again. And we'll have a 5-minute break before the next speaker.